Hey, ever wondered how an AC generator works? How it magically transforms mechanical energy into electrical energy? It's a question that's piqued the curiosity of many, from budding engineers to everyday tech enthusiasts. AC generators or alternators are a marvel of engineering, right at the heart of our power supply. They're the silent workhorses that keep our world electrified, yet their inner workings remain a mystery to many. Well, it's time to lift the veil. Today, we'll demystify the workings of an AC generator. An AC generator or alternator is a marvel of engineering. Let's start with its construction. At the heart of the generator is the rotor, a coil of insulated copper wire mounted on a shaft, which is free to rotate. This rotor, often made of many turns of wire, is the heart of the action, the place where mechanical energy gets converted into electrical energy. Now, this rotating rotor needs a dance partner, and that's where the stator comes in. The stator is a stationary set of coils or magnets that produce a magnetic field. This field remains fixed relative to the rotor and provides the magnetic field lines that the rotor will cut through as it turns. But how does the current get from the rotating rotor to the stationary external circuit? That's where the unsung heroes of our story, the slip rings and brushes, come in. Slip rings are rings mounted on the rotor shaft that maintain electrical contact with the rotating coil. Brushes, typically made of carbon, ensure continuous contact with the slip rings. Together, they transfer the generated current from the rotating rotor to the stationary external circuit. So, we've got a rotor cutting through a magnetic field, generating current, and slip rings and brushes transferring that current to the external circuit. But what happens next? Well, the rotor doesn't just sit there. An external force, perhaps a turbine or an engine, rotates the rotor. As it spins, the rotor cuts through the magnetic field lines. This induces an electromotive force, or EMF, in the coil according to Faraday's law of electromagnetic induction. As the rotor continues to spin, the direction of the induced current changes periodically. This results in the generation of an alternating current, or AC, in the coil. The AC is then transferred to the external load circuit via the slip rings and brushes. The frequency of the AC depends on the speed of the rotor's rotation and the number of magnetic poles in the stator. Voltage control can be achieved by adjusting the strength of the magnetic field, the number of turns in the coil, or the speed of rotation. Understanding the construction is vital to understanding how an AC generator works. Now let's dive into how an AC generator works, starting with the initial position and rotation of the rotor. The heart of the AC generator is the rotor, a coil of wire that's free to rotate. Initially, this rotor is positioned to cut across the magnetic field lines created by the stator. The placement is strategic. By setting the coil at an angle to the magnetic field, the change in magnetic flux is maximized as the rotor rotates. But what causes the rotor to rotate? That's where an external force comes into play. This could be anything from a turbine driven by wind, water, or steam, to an engine powered by gasoline or diesel. When this prime mover kicks into action, it spins the rotor, causing the coil to cut through the magnetic field lines. Now, here's where things get interesting. As the coil slices through these magnetic field lines, an electromotive force, or EMF, is induced in the coil. This phenomenon is a direct result of Faraday's law of electromagnetic induction, which states that the induced EMF in a circuit is directly proportional to the rate of change of magnetic flux through the circuit. As the rotor continues to spin, it keeps cutting through the magnetic field lines. This constant movement and interaction with the magnetic field means the EMF in the coil is continually induced. But there's a catch. As the coil rotates, the direction of the induced current changes periodically. Why is this important? Well, this changing direction of current is what gives us alternating current, or AC. Unlike direct current, which flows in one direction, alternating current switches direction periodically. This is why it's called alternating. In essence, the AC generator is a beautifully choreographed dance of physics and engineering. The initial position of the rotor, its rotation, the cutting of the magnetic field lines, and the induced EMF all work together to produce alternating current. This rotation is what sets the stage for the generation of electricity. After the rotor starts rotating, something remarkable happens: the generation of alternating current. The rotor, with its coil of wire, is now slicing through the magnetic field lines like a hot knife through butter. This relative motion between the rotor and the magnetic field results in an electromotive force, or EMF, being induced in the coil. This is all thanks to Faraday's law of electromagnetic induction. which states that a change in magnetic flux can induce an electromotive force in a circuit, and it's this induced force that gives rise to an electric current in the coil. But here's the twist. As the rotor continues to rotate, the direction of the magnetic field through the coil changes. When the coil is vertical, it's cutting through maximum magnetic field lines, so the induced EMF is at its peak. But as the coil rotates and becomes horizontal, it's no longer cutting through the magnetic field lines. The EMF drops to zero. Then, as the coil begins the second half of its rotation, it starts cutting through the field lines again, but in the opposite direction. This induces an EMF in the opposite direction. The coil returns to the vertical, the EMF peaks again, but negatively, and then, as the coil returns to the horizontal, the EMF drops back to zero. This constant change in direction of the induced current is what gives us alternating current, or AC. The current reaches its maximum in one direction, drops to zero, reaches its maximum in the opposite direction, and then drops to zero again. And this cycle repeats over and over, in sync with the rotation of the rotor. This alternating current is the output of the AC generator. It's this current that can be used to power your home, your city, and beyond. And all of this, the magic of alternating current, begins with a simple rotation. The conversion of mechanical energy into electrical energy, the dance between the rotor and the magnetic field, the birth of alternating current. It's a symphony of physics, and it's happening right now in generators across the world. The generated AC doesn't stay inside the generator, it's transferred and controlled. Let's talk about how this happens. The alternating current, or AC, that's been generated within the rotating coil doesn't just sit there. It's transferred to an external load circuit. This is where the slip rings and brushes come in. These components are key players in the process, acting as the bridge between the rotating coil and the external circuit. The slip rings maintain electrical contact with the rotating coil, while the brushes ensure continuous contact with the slip rings. Together, they ensure the smooth transfer of AC from the generator to where it's needed. But it's not just about transferring this AC. It's also about controlling it. Two important characteristics of the AC are its frequency and voltage. These need to be controlled to suit the requirements of the application the AC is being used for. The frequency of the generated AC is dependent on two things: the speed of rotation of the coil and the number of magnetic poles in the stator. By adjusting these variables, one can control the frequency of the AC. Voltage control, on the other hand, can be achieved in a few different ways. One way is by adjusting the strength of the magnetic field. More magnetic field strength, more voltage. Another way is by adjusting the number of turns in the coil. More turns, more voltage. Lastly, the rotational speed can also play a part. Faster rotation, more voltage. So this is how the AC is transferred and controlled. It's a process that involves not just the generation of electricity, but also its efficient transfer and precise control. And it's all accomplished through the principles of electromagnetic induction and the clever design of the AC generator. And that's how an AC generator works, from start to finish. We've covered a lot, so let's recap. We've delved into the fascinating world of AC generators, or alternators, and how they convert mechanical energy into electrical energy. We've seen how these devices are constructed, with a rotor, stator, and in some designs, slip rings and brushes. The rotor, a coil of wire mounted on a shaft and free to rotate, cuts across the magnetic field lines produced by the stationary stator. When an external force rotates the rotor, the coil cuts through these field lines, inducing an electromotive force, or EMF, in the coil, as per Faraday's law of electromagnetic induction. As the coil continues its rotation, the direction of the induced current changes periodically, which results in the generation of alternating current. This current is then transferred to an external load circuit through the brushes and slip rings. We also explored how the frequency and voltage of the generated AC can be controlled. The frequency depends on the speed of rotation of the coil and the number of magnetic poles in the stator, while the voltage can be adjusted by varying the strength of the magnetic field, the number of turns in the coil, or the rotational speed. This understanding of AC generators is fundamental to our modern electrical power systems. Next time you switch on a device, remember the AC generator that makes it all possible. If you like the content, please like and subscribe to our channel, and don't forget to click on the bell icon to get new video updates.